In this video, we're going to review the idea of quantiles as the inverse cumulative distribution function, how we can use that to generate, or how to generate random numbers actually, and how we can use quantiles and random numbers to generate random data of a particular distribution. To begin with, we'll start with our SMAT Studio file, where we indicate that when we're given a cumulative distribution function f of x that corresponds to a probability p prime, we're given the value of p prime, which should be a value between 0 and 1, then the inverse function produces what is called a quantile. To illustrate some examples, we provide here the parameters of a binomial distribution, and then we create a vector of probabilities going 0.1, 0.2, and so on. And then we use the inverse cumulative distribution function for the binomial distribution with the vector p prime, parameters n and p, and we vectorize that. Remember, to vectorize, we use this particular function in the matrices palette. And then it gives me, actually put together a matrix consisting of the probabilities from 0.1 to 0.9 and the corresponding quantiles obtained with the inverse cumulative distribution function. And when we plot that, is this stair type of graphic. We can see a similar result for a Poisson distribution. Again, that increased stair type of graphic for a geometric distribution. Similarly, for a geometric shifted distribution, similar idea. And with a geometric, actually, I should apologize. This is not the geometric shifted. This is the uniform discrete distribution. And for which we obtain this type of a graph. Now, those are quantiles, and quantiles have some applications, but one of the most important ones is in the generation of random data. We have a function in the Statistical Tool plugin called random. When you call that function with a single argument, like 5, it gives you a vector with that number of elements, where each element is a number between 0 and 1, which is like a probability, right? If you use 2 arguments, that will give you rows and columns of a matrix. Now, every time that you recalculate a page, like I show you here, you recalculate, those random numbers get changed because the random number generator is active all the time. Let me show you again. So if you want to use a particular set of random numbers, you have to copy that and store it in a variable. I did this a while ago, but I can show you how to do it. You just got to select the right-hand side, do Control-C to copy, and make it into the right-hand side of a particular variable. Now, this simple linear relationship will convert this matrix of values between 0 and 1 into random numbers between A and B being a couple of numbers, A less than B. For example, if I take A equal 10 and B equal 20, I'm going to produce these random numbers. If you want integer numbers, you can use the round function applied to the last result with 0 decimals, and you get integer numbers. A more direct way to get integer numbers is to use the inverse cumulative distribution of the uniform discrete for the values of A and B. You can see that this matrix and this matrix, both generated using this RO1 set of random numbers, are very similar, but there's a slight discrepancy, and that could be just a numerical error. And you can see here. Now it's pretty much, well, there's a difference between the first one, 11 and 10. All right. So there's another function called random.n, where you can provide a number of rows, number of columns, the initial and final values out of which you're going to find your random numbers, which are integer. Okay. If you use 3 arguments only, the first argument is the length of a vector, and they are all integer. If you use 2 arguments only, it will give you a single number that is integer. You can use the function random 1 with subindex 1 to give you a random number between 0 and 1. Now, if you want to generate random numbers that are decimals with a certain number of decimals, you can use this trick. Produce a number, for example, random n between 0 and 100 and divide by 100, and it gives you 2 decimals. 1,000 and divided by 1,000 give you 3 decimals. 10,000 over 10,000 give you 4 decimals. Okay. A general procedure for obtaining random numbers from a given distribution is as follows. Generate a matrix of random numbers like random 3, 4. Then use the inverse cumulative distribution for a uniform discrete, for example, to give you the random number that you're looking for. You can try with a binomial distribution. You just have to use the inverse cumulative distribution function for a Poisson geometric. These are all discrete, but you can also do the same for continuous. So how do we use random numbers? Suppose that you generate a matrix of 3 by 5 integer random numbers on the Poisson distribution. And a second simulation will give you different values. Suppose that you are modeling a statistical or a random variable that follows the Poisson distribution. You get 2 sets of Poisson distribution there to use in your model. These are called Monte Carlo simulations. Monte Carlo is the capital of the Principality of Monaco, which is located in the Mediterranean and is also surrounded by France. And they operate big casinos there, and casinos are where random numbers are continuously being generated. And so, to honor that city, when you produce random data to use in simulation, they are referred to as Monte Carlo simulations. We're going to do some histograms here, so I'm going to insert the statistical and graphic functions. Remember that's done using Tools, Snippet Manager, and you should have that statistical and graphic functions. And I'm going to generate a random set of 10 rows by 10 columns between 0 and 1. And then I did a previous one, and I copied that and stored it into a variable R, so it will not change. Then I generated a weighable data using the inverse cumulative distribution function for that set of random numbers between 0 and 1, with my parameters beta and alpha for the weighable distribution being 2.2 and 5.2 respectively. And that gives me a certain vector of data which follows the weighable distribution. If I use the function AllStats for that particular random data set that I call uppercase X, I get all these statistics of these, in particular the minimum value being 0.72 and the maximum 3.16. So I selected being starting at 0.5 and ending at 3.5, separated by values of 0.3, and these beans are going to be used for a histogram. I did one thing that I haven't done before in the examples of histograms, and that's the box plot. And the box plot has its own function called box wplot. You have to provide the data set, then the value of y along which the center line of the box is going to be, which is a y equals 0 here, and this is the width of the box, which is 1 unit in each side. Okay, and then I call the function frequency tx for my matrix of data x and the vector of beans x bean. It gives me 0, 0 outliers. I extract the first element. I call it freq. And out of that frequency, I extract the fifth column as my x data. And then I produce my bar plot, which is the histogram. To produce a normal distribution to go on top of that, I obtain the mean value of my data, the standard deviation, and the total area under the bins, and produce this normal distribution Fn, which then I plot together with my histogram. And remember, this data is weighable, and so it doesn't quite fit the normal distribution. All right, so you don't expect this to be a symmetric distribution that approximates the normal. You could try this exercise with other distributions and adjust the histogram accordingly. Here we did weighable, But we could try, for example, let's see, a normal distribution right here. And that gives me some negative values, and so it's going to change my picture of the x values here, because the minimum will go between minus 15 and 20, let's say. And so we got to change our x-axis to a minimum of, say, minus 15 and a maximum of 20. Oops, sorry, 20 in increments of 5. Okay. And now my box plot looks better. The beans now will not be like these. I'll have to figure a different range. I'm gonna call it X bean range, and we're gonna start now with like let's say minus 10, and go up to 15, and incrementing every 2. I'm going to delete this one and see what we get here. I'm going to put an equal sign right to the right, and we end up, oh, okay, sorry. I should have put something like minus 8 here. That's too many. I'm going to go for a minus 7, for example. So instead of going up the way to 15, I'm going to go to 14. So let's see what we get from that. We have our frequency distribution. We extract the top matrix. We extract the X data. Now, remember that our beans now go from minus 10 to 14, so we need to adjust the x-axis here from minus 10 to 14. Oh, sorry, I accidentally put 314. And in increments of, say, 2. Okay, so that's our histogram now. And next we have I'm going to change my x-axis here. I realize I may have a problem because of those negative values. Minus 10. And we do now a recalculate page. Oh, well, it actually gave me, I want to change for the x-axis the increments to 2. It gives me a normal distribution that sort of follows the histogram. And so, in that way, we have repeated our calculation here using a different distribution. And with that, you may want to follow